Assalamu alaikum. I am Saiyem Raiyan. We write a review paper on neuromorphic computing. I will be starting with our group introduction first. We have our 4 members in our group, uh, consisting of Sheikh Mohammed, Wali, Ullah, Ayman, Ibne, Hakim, MD Tamjid Hossain, and me, MD Saiyem Raiyan. Now I will talk about the project topic, neuromorphic computing. So mini review of neuromorphic computing, and that's presented by myself. Introduction. So our brain is an enigma and it remains one of the great frontiers of science, the 1.4 kg fatty material that we have carry on our heads that defines on personalized stores and memory and control all aspects of our behavior. Most hardware today is based on the von Neumann architecture and that separates the memory and computing. Because of von Neumann chips, we have shared information back and forth between the memory and CPU, the waste of time and energy. The problem is known as von Neumann bottleneck. So as time goes on, the von Neumann architecture will make it harder and harder to deliver the increases of computer power that we need to keep up. We need a non-von Neumann architecture, which is needed to be a neuromorphic architecture. So the term of neuromorphic computing is used to more broadly to set a brain-inspired hardware and algorithm to neural network with varying degrees of biological possibility. Advances in microchip technology have followed Moore's law that has been reducing the transistor size, and CMOS transistors are made smaller. They become the cheaper, faster, and the more energy efficient, powerful, and mobile computer technology. Basically, the goal of neuromorphic computing is to observe the medieval complexity of biological brain and somehow extract from known its structure and principal operation of practical engineering system. Then the theory parts. Neuromorphic computing is a method of computer engineering that which elements of computing model after system in a human brain and nervous system. The term refers to the design of both hardware and software computing elements. Neuromorphic engineering draw the several disciplines including computer science, biology, mathematics, electric engineering, and physics, and so on. The von Neumann computer compromised to separate processing the memory and quiet data and instruction are stored in a later in concept neurostructural computer and processing and the memory are controlled by the neurons and synapses. The neurobrain computing work as based as a model of human nervous system as computational neurocomputing simulate the engineering of a computer in a way includes millions of artificial silicon neurons capable of transmitting electromagnetic pulse from each other. Then I discuss the material methods. Perception, neurogrid, spin maker, and brain skills. First of all, perception is consisting of a single neuron or a simplest from like biological neurons with axon and dendrites. A single artificial neuron is a simple structure with the input node and the one output node connected to each input node. There are 4 parts: the input node, weighted and bias, the weighted sum, and the activation function. Its work as a taking specific numeric input is so-called wedges, and the activation function takes the sum of the wedges and the output offset of the inputs and the returns of the final output. Then the multi-layer perception is a more complex network than cognition because they are made up of several neurons organized in layers. The layers are fully connected to each other. This overcome the limitation and also represent a more complex in decision. Then the neurogrid. Neurogrid is basically specifically designed to the simulate biological brains and the system capable of simulating of 1 million neurons in a real time. The real-time operation of a neurogrid makes it suitable for robotic control. Then the spin maker, which is an open source computer architecture inspired by the working as a human brain. The machine is massively parallel computing platform that focuses on the 3 main areas: research and neuroscience, robotics, and computer science. It uses in many fields like robotics, machine learning, computational, theoretical neuroscience, and visual processing, and even art, the simulate of the slice of a cortex of a rat like biological fact. Then the brain skills. It aims to understand and simulate the function and the interaction, the multiple spatial and the temporal scale of the brain transformation in processing. The control computation cluster arranges the system configuration and perform neutral and network tests, including all input and output data of simulated works. As the supporting infrastructure is responsible for power supply, the off-wafer communication, and the analog playback functionality. So that's all from me. Thanks for listening to me. Then I hand over the next presentation to Sheikh Mohammed Wali. Thank you.
Hello, I am Sheikh Mohammed Wali. In this presentation, I'll be talking about my contribution in this project, a review on neuromorphic computing. In this slide, you can see my contribution in these different parts of the project. I will talk about all these things in this presentation. Firstly, I will talk about human brain versus neuromorphic system. In neuromorphic system, for somata, we use Neuristor. For dendrite, we use shortware. For axon, we use longware. For synapses, we use Memristor. I will talk about some properties of neuromorphic computing in this section. First, I will start from spiking. In neuron, communication happens using voltage or current spiking, rather than using continuous signal in typical digital electric system. Plasticity. It allows neuromorphic circuits to be modified as they are exposed to different signals. The device gives response based on history of circuits. Dynamic resistance. It is an activity-dependent synaptic plasticity where correlated activation of presynaptic and postsynaptic neurons results in strong connection between two neurons. Adaptability. It means learning to handle situations. Neuromorphic circuits go through a learning process to handle critical situation so that the circuit can be more fault tolerant. Criticality. The system needs to be able to explore many closely lying critical points. There can be some critical points like phase transition. Accelerator. The machine require intermediate steps to think about work, better algorithm to speed up. Some applications require the contribution of various sensors in with some computations. In results and discussion parts, I will start from the health sector. In health sector, insulin system can read the glucose level in body and push the required insulin to the body using neuromorphic computing. Research. Machine designed by neuromorphic computing can do the rigorous calculation accurately in a short time, like vector matrix multiplication, pattern matching. Industry. Machine designed with neuromorphic architecture can easily detect errors and also can manage tasks. Imaging. We can design high-level vision sensors that can detect light intensity of pixels rather than frames. Artificial intelligence. We can design better machines or robots by collaborating neuromorphic computing with artificial intelligence. This was all about my presentation. I am giving the floor to Ayman Ibne Hakim.
Assalamu alaikum. I'm Ayman Ibne Hakim, and I will now discuss about my contributions on a review on neuromorphic computing. For materials and methods, I've discussed about memristors, which is one of the most fundamental materials used in neuromorphic computing. It can emulate synapse functionality in a single device that is small and scalable. It can be configured in crossbar arrays that can make very dense network connectivity possible. The memristor is non-volatile, which means it can hold data even after power is turned off. CMOS spiking neurons. It is possible to develop neuromorphic, very large-scale integration systems that simulates the computing occurring in a brain cortex by utilizing memristor synapses integrated on a regular CMOS chip. A CMOS spiking integrate and fire neuron IFN circuit naturally is a two-port neural network building block. To develop a large-scale brain-inspired computer architecture, the proposed CMOS IFN provides a basic foundation for the seamless integration with nano-scale resistive synapses. These designs are intended to usher in a new era of energy efficiency and real-time machine learning. Now let's talk about a few applications. Event-based vision sensor. The event-based vision sensor is a new machine eye that mimics the human eye mechanism. In a conventional frame-based sensor, all pixel information is recorded in each frame, but in an event-based sensor, it reacts to pixel with luminance changed by the movement of the subject. An event-based sensor will enable us to produce higher resolution image and eliminate motion blur. This can be used in liquid monitoring where the liquid is captured as droplets instead of fluid. Human tracking, which can work regardless of the lighting condition, vibration monitoring, and 3D measurement. Another application would be the odor recognition system. Scientists are trying to replicate the human characteristic of odor recognition in machines. With the help of neuromorphic chips, it is possible to create odor recognition system that can recognize scents on the basis of this circuit diagram and the electrical pulses. A set of algorithms can be derived and configured on neuromorphic silicon. Another application would be the closed loop control system. So a closed loop control system is a set of mechanical or electronic devices that automatically regulates a process variable to a desired state or set point without human interaction, which means it works without any manual input. Closed loop control systems are used in agriculture sector, water treatment, nuclear power plants, etc. Closed loop systems enable automation in industrial and environmental settings and regulate processing in industry like supervisory control. All of the applications discussed can be improved by further research and will hopefully help us come up with more applications on a wider scale. Thank you. And now I would like to give the floor to MD Tamjid Hossain.
Hello sir, Assalamualaikum. This is Tamjid Hossain. In this part of the video, I will talk about a chip that's already been invented by IBM, and in the later I will discuss a little bit about neuromorphic computing and its future uses. Then I will give you the closing remarks. So the IBM has already invented a neuromorphic chip called True North. It has over more than 4,000 cores and 256 neurons. Each of it contains 256 synapses. It has one of 10,000 of power density of a classical von Neumann processor. It achieves its efficiency through a sparkling neural activity, and the activity only occurs when and where it is needed. This whole process makes the chip particularly suited to high speed and lower power consuming image for image processing and calculation tasks. So the solution of power consumptions lies in the more efficient designs of more efficient circuits and with obviously lesser power consumptions. And if we collaborate AI with the concept of neuromorphic computing, we will have better algorithms and different calculation techniques, and we will be able to perform many other difficult tasks. The neuromorphic computing can be used in the future in the health sector, weather forecasting, and detecting faulty machines in the industry. And with the help of AI, we will be able to build better and more advanced machines. So we can say the future of computation lies in the field of neuromorphic computing. With the mass application of this technology, the world will see changes it never did before. And with more sheer determinations, more researches, we will soon be ready to see this outbreak. Thank you very much.